electrical and electronics engineering building and extended to area being the cafeteria. The path included both straight and furrowed sections, offering a suitable scenario to evaluate the accuracy of the state estimation algorithm.
And as you see, this is the block diagram that we have that are given the sensors, the GPS giving 5 Hz position data, and INS gives the accelerometer data around 100. While using these data, we have run the unscented Kalman filter around 30 Hz. Our estimated stays updated 30 Hz. That is why. And the algorithm and data processing are implemented in real-time application, distinguishing in this work other projects that rely solely on CSV data for online analysis. We have done our algorithm in runtime, which differs from the other projects, which are offline project, while reading CSV reading data from the CSV and then run the algorithm. As you see, this is the picture of the in runtime application. This is the our university campus, and this is the trajectory that we track while we're having the Kalman filter. And please go ahead, Tom.
To conduct a real-time unscented Kalman filter experiment, callback functions or INS and GPS data are implemented to process incoming data dynamically. When GPS data is not available, the algorithm performs only the prediction step. On the other hand, if INS data is unavailable, the correction step is executed instead. In cases where neither GPS nor INS data is accessible, the predicted states are directly assigned as the current state, ensuring seamless state estimation. Figure 3 illustrates the C++ implementation that manages the sensor availability conditions, highlighting the robustness and reliability of data processing system in real-time application. Keep going, please.
These are the results that are plotted by using the MATLAB and M functions. This is the filtered data. The first plot is the filtered data, and these are the parameters of the unscented Kalman filter. Alpha is 1, kappa and gamma is 2. This is the raw data. As you see, our filtered data is the number of the filtered data is highly increased because of we have run the algorithm around 30 Hz, and this is the Y filtered and Y raw data plots. It seems that there is a differences between the filtered and raw. And this is the X filtered and the X raw data that we have done the trajectory that we have used the data on our campus. And these are the plots of the differences between X filtered and X raw under these parameters of the unscented Kalman filter. And this is the variance of the position of X and variance of the position of Y. The Y position, the variance of the position of Y is seemsly decreased, but there is a increased process after all the data full on the unscented Kalman filter. And these are the 2D trajectory on same pilots. The blue one is the filtered data. The red one is the raw data on our campus. And limitations. Please go ahead.
Dependency on GPS signals. The accuracy of the state estimation is highly dependent on the availability and quality of GPS signals. In areas with poor GPS reception, such as densely built urban environments or heavily wooded regions, the reliability of the update state decreases, which can result in drift in the estimated states. Second, image noise and bias accumulation. Although image data is provided at high frequencies, it is susceptible to noise and gradual bias drift. In the absence of the frequent GPS corrections, errors in the predicted state may grow over time, particularly during extended periods without GPS updates. Thirdly, controlled data collection environment. The data used in this experiment was gathered in a controlled setting at the Yıldız Technical University campus. The findings may not fully apply to more challenging or dynamic terrains where abrupt motion changes or varying environmental conditions could impact the system's performance. Let's go.
And to sum up everything that has been stated so far, this study presented to design the implementation of an unscented Kalman filter for state estimation using the sensors, which are GPS and INS system. By leveraging the high-frequency internal measurement data for the prediction step and the accurate but low-frequency GPS data for the update step we have used. And the system achieved reliable and accurate state estimation around 30 Hz. The key contribution and findings are summarized as follows. Enhanced accuracy with multi-sensor fusion, improved state estimation frequency. These are the contribution that we have done while we having the lectures. And the future work, as you see, the data is full. The data have a constant acceleration model and turn model, and as you see, the velocity model. After we done the unscented Kalman filter, we have seen that by using just one constant process model is not sufficient for a real-time application. That is why we are going to analyze and implement the adaptive Kalman filter thanks the part of the interactive multiple model of the Kalman filter will be implemented and evaluated using the same sensor setup, allowing for a direct compression with the unscented Kalman filter approach. This compression aims to evaluate the effectiveness of IMM in handling scenarios with varying motion dynamics and process model transition, further improving the accuracy and robustness of the state estimation system. Thank you for listening.